Hello everyone, welcome to this video. In this video, we'll be learning about the properties of subgroups under homomorphism. So in the previous video, we saw under the mapping phi from some group G to some group G bar, right? How the elements behave under this mapping if this mapping is homomorphism, right? Now let's consider some subgroup H from this group, right? So we will see how and what properties of this subgroup relate to its image here in G bar. Right, so that is what I have written over here. If phi is a homomorphism from the group G to G bar and H is some subgroup of G, then the first property here tells us that the image of this subgroup H is what? It is also a subgroup of G bar, correct? So here what is the image? It consists of all the members phi H such that this H is a member of the subgroup capital H, right? So it is already known to us that H is a subgroup of G, right? We have to prove that phi of H is also a subgroup. So because H is a subgroup, so if you take any two elements within it, A and B, right? So by the one step subgroup test, you know A B inverse is also present in H, correct? Now if you take two elements, because A and B are present in H, so if you take their images phi of A and phi of B present in phi of capital H, right? So what would be this element? If this element is also present here, then we would say it is a subgroup by the subgroup test, otherwise not. So you see phi of A, phi of B inverse, what is it? It is phi of A, phi of B inverse. You can take this inverse inside. Why? Because phi is an homomorphism and by the operation preserving property it is written like this. Next, you can club up the terms here. You can combine A and B inverse. Why? Because again, using the operation preserving property of homomorphism, it is phi of A B inverse. Now A B inverse, you know, is a member of H. So phi of A B inverse would also be a member of phi of H by the definition given to us here. So therefore we are able to prove that if phi A and phi B are two different elements from phi of H, then phi of A into phi of B inverse is also present in phi of H, correct? So this is our first property. Hence we can clearly say that phi of H is a subgroup of G bar. For the next property, if we consider H to be some cyclic group and phi of H to be, we wanted to prove that phi of H is also cyclic, right? So we first of all consider H to be cyclic group with generator H, right? Now if we take some element Y from this image phi of H, right, then we wanted to prove that the phi of H is also cyclic. So we are able to write, we wanted to prove that we are able to write Y as some power of some power n of some member, correct? So here we consider Y from this subset phi of H, right, which is also a subgroup. Now if Y is present in phi of H, so that means there exists some X in this capital H such that you can write it like this: Y is equal to phi of X by the definition, right? So by this definition, so therefore you can write Y is equals to phi of X. Now because X is present in capital H subgroup and because we have assumed this to be cyclic with the generator H, so therefore you can write X as some power of H, correct? For where this power is some integer. So you can write Y, which is phi X. Now you can write X as H raised to power n using this relation, right? And then now using the order operation preserving property of phi, because it is a homomorphism, you can write phi H of n as phi of H whole raised to power n, correct? So therefore, because Y was some arbitrary member such that Y could be written like this for some X, then phi of H becomes the generator of phi of H, and hence this is also cyclic in nature, and this is the second property we wanted to prove here. So I hope you understood these two properties well. Well, that is it for this video. Thank you for watching.